So this course will be on kind of Malliavin calculus. And so this is, perhaps some of you have heard this, this notion. It's a stochastic calculus, which essentially for kind of an analyst like me means taking the derivative with respect to the noise, which typically will be something like white noise, but we'll get to it eventually, so you don't have to know it. And I want to apply this to kind of a recent, so this is kind of mathematics. I don't know when that was introduced. Actually, I should know, but I would say perhaps 30 or 40 years ago. But I want to apply it to what is called regularity structures. And this is something much more recent, so the first thing is attached to the name of Paul Malliavin, who was professor in the University of Paris, Paris 6. And the second notion is attached to the name of Martin Heira, who introduced this kind of toolbox to deal with stochastic partial differential equations. And but again, you don't have to know that, because I will try to give kind of a soft introduction into that set of ideas with a little twist, which is somewhat different from how it's originally done. So, I mean, as opposed to the two other speakers, I didn't finish lecture notes in time, but they will become available as I go on. And if you're interested, they will be posted, in a certain sense, on the daily basis on my webpage. So I wrote it down. So Aplan, which stands for Applied Analysis, lectures, and then summer term. (2023) HTML. And there I mean, in principle, probably by now, the first couple of pages are already posted, which will cover certainly probably more than I will manage to be able to do today. Okay, so after these remarks, let me start. So the first section or the first chapter is on kind of motivation and setting. And this will be about kind of partial differential equations. So I have to start by kind of specifying a differential operator. So the differential operator we will be working with is something which I hope many of you are already familiar with, namely it's the heat operator. So this is, I will denote it by L. That's the time derivative, del 0, minus the sum of the squares of spatial derivatives. So where di is the partial derivative with respect to the variable xi, and so this is a differential operator on Rd plus 1, 1 plus d. So x0 is the time-like variable, and those are the space-like variables. And I'm using this notation with 0 and 1 up to n, up to d, because in the end, the time will not play such a different role from space, and therefore it's convenient to have x denote both time-space variables. So x0, x1 up to xd. So that's the time-like variable. Those are the space-like variables. And that's a second order, because of the square here, is second order partial differential operator. And it's called parabolic because the polynomial in the partial derivatives, which defines this operator, would have a kind of a null set, which is given by a parabola. And I think many of you will know it as the heat operator, where this here sometimes is also written as the Laplacian. Okay, so this is the operator L. And now we're interested in the following partial differential equation. So given a parameter lambda and a space-time function psi, we consider the nonlinear partial differential equation, which is given by L phi minus lambda phi cube is equal to psi in the entire time space. So if lambda is equal to 0, we're just, in a certain sense, solving the heat equation with the right-hand side, which is given by this function psi. And if lambda is not equal to 0, this is, we have this cubic nonlinearity. It's a nonlinear equation. And in this entire course, I will always focus on solutions which are entire solutions, so which are in the entire space-time. So that's important. I always mean that, even if I don't, if I shouldn't write it explicitly. So in fact, we're interested in the solution manifold. So we're interested in the solution manifold. So in all the functions, in all the space-time functions phi, which satisfy equation star. So that's another somewhat perhaps unusual feature that we really want to understand the entire, obviously, nonlinear solution manifold. And so that's something to keep into mind, where we'll never be interested in one specific boundary or initial value problem. We'll be interested in kind of the entire manifold, the entire space of solutions. And we're interested in this in the situation when this right-hand side is rough. So what does one, or what do I mean by rough? So by this I mean that phi is, xi is no longer a function, but just what is called, and I will explain what that means, a Schwarz distribution. And so let me explain what it means to be a Schwarz distribution. In order to explain what it means to be a Schwarz distribution, I have to explain what it means to be a Schwarz function. So the space of Schwarz functions zeta. So zeta will always denote a generic Schwarz function. Psi will denoting kind of our right-hand side, is the linear space of those infinitely differentiable functions zeta that, perhaps I can squeeze it here, that decay fast enough such that the semi-norms which are given by the following expression. So you take a possibly very high derivative of your function zeta. By this I mean, like is usually done, this combination of partial derivatives where this multi-index n is something in as a space-time multi-index. So we look at a potentially very high partial derivative of zeta. We take the soup norm, but then we put a huge weight in front of it in order to monitor the decay. So we want these expressions to be finite for every exponent k, which of course we can assume to be an integer, and for every multi-index n. So that means these functions are extremely smooth because they're infinitely often differentiable, but not only are they infinitely often differentiable, they decay faster than any power at infinity. So those are called Schwarz functions. So that's not the Schwarz of Cauchy-Schwarz, but Laurent-Schwarz. Those are Schwarz functions. And so those are kind of extremely nice functions. And a Schwarz distribution is kind of the opposite. It's something which acts on Schwarz functions, so it's something which potentially is very rough. I will give you an example in a second. So it's something in the dual space on Schwarz functions. So distribution, a Schwarz distribution is a bounded linear form xi on the space of Schwarz functions. And I will denote the duality product by xi comma zeta. And boundedness means that that there is that this expression can be estimated by a finite combination of these semi-norms. So that's the definition of a Schwarz distribution. And now let me right away give a relevant example. So a relevant example for d is equal to 0. So d equal to 0 sounds a bit strange, but that essentially means we just have the time variable. So it's meaningful. So we're in a one-dimensional setting. So for d equal to 0, consider Brownian motion. B, which we consider as a function of x0, which is our time-like variable. Then if I define a distribution xi in the following way by setting this expression to be equal to minus the integral over time of Brownian motion against the derivative of the test function, the Schwarz function zeta. So let's consider a realization. Of Brownian motion. So I fix some realization by B0 of Brownian motion. And I claim that this defines a distribution. So, okay, obviously this defines a linear form. I mean, this expression which I wrote down is linear in zeta. That goes without saying. Now, why is it bounded? It's bounded because of the law of iterated logarithm. we know that this expression here can be estimated. So we know that Brownian motion doesn't grow faster than the square root of x0 up to a logarithm, or up to a double logarithm. So we can certainly estimate this expression by up to some constant, which is random and depends on the realization, by the sup over x0 of 1 plus x0 times the first derivative of zeta at x0. And that's one of the norms here, where k is equal to 1, and this here is just the first derivative in the time-like variable. So this defines a distribution, and this distribution has a name. So sometimes one writes this I wrote a minus sign for a reason, because it should suggest that here in principle you can do an integration by parts. And if you do an integration by parts, you may interpret this definition as saying that you define this distribution as the derivative of Brownian motion. So that's a formal way, but very helpful way of rephrasing this identity. And this derivative of Brownian motion goes with a name. It's called white noise. So it's temporal in this case. Temporal white noise. And this is not a function. Why is it not a function? Because Brownian motion doesn't have finite total variation. So psi is not a function, by which I mean it cannot be written in the following form as an integral against some locally integrable function zeta, f times zeta, for some locally integrable f. Since if I could do that, I would learn that Brownian motion has finite total variation, which it doesn't have. So this is an example of a distribution that's not a function. And actually it's a very relevant example for us, because in a second I will extend this notion of white noise from just a single variable to, so just temporal white noise, to space-time white noise, which is kind of a typical example of psi we want to take. Are there questions so far? Am I speaking loud enough? Okay, yes?
Yeah. I don't understand the meaning of zeta equal to differential Brownian motion by dx0, because sometimes you say the Brownian motion is not differentiable.
Yeah, that's exactly what we're using here. But you can take what's called a distributional derivative of a distribution. And a distributional derivative is exactly defined like this. So, given distribution, so Schwarz distribution psi, we can take any derivative and so, for example, if you define Let me take the partial derivative with respect to the first spatial variable of psi. So I want to tell you how to define this distribution. You define a distribution by saying how it acts on Schwarz functions, and you define it to act as if in this pairing you could do an integration by parts, so minus psi del 1 zeta. So it's a definition, and that's called a distributional derivative, and it's a very important notion in partial differential equations with rough data, because it allows to give a sense to PDE even if you're not dealing with functions but with more irregular objects. So in this sense, and it's very important to think like this somewhat intransparent definition can be interpreted as saying psi is nothing else than the distributional derivative of Brownian motion. And because, as you say, Brownian motion is not differentiable, it's not classically differentiable, it's even not of finite total variation, what you get is not even a locally integrable function, but it's genuinely a distribution. More questions? Yes?
That K over there in the definition in the sum.
Yeah?
Are we taking a supremum over K, or K is equal to the sum of?
No, so in a certain sense, this expression defines for every K and every N a norm, a semi-norm. It's just a semi-norm because it's blind to constants if I take a derivative. And now the space of Schwarz functions is defined as the set of functions for which all these semi-norms are finite. So it's not a Banach space because there is not a single norm, but there is a whole family, a bag of norms. But I will not do functional analysis here for you. So that's what it means. So there's neither a sum over K nor a sum over N. More questions? Yes?
I'm just wondering if the derivative and the definition of the semi-norms only concern the derivative on space variable is.
Sorry, that's a typo. It should start at 0. Thank you. More questions? Okay, so let me continue in this vein, because we're even interested in the worst situation, where not only the right-hand side is rough, but any putative solution is rough. So let me be a bit more precise on this. Perhaps I'm going to erase this here. So, interested in even worse situation, namely in the situation where any solution of the linear equation is not a function. How can we cook this up? That's not hard. Again, let's look at the case when there's just the time variable. It suffices to take psi to be, in a distributional sense, not just the first time derivative of Brownian motion, but the second time derivative of Brownian motion, which, of course, again, is a distribution. But now it's clear that if we consider this equation for lambda equal to 0 and for d equal to 0, which means we're just looking at this equation, and let me call, because I will continue to do so, solutions of the linear equation by a capital pi 0. That's eventually the notation which Martin Heira uses, so we have to accept it. So let's consider a solution of this linear problem. So since I defined the right-hand side to be the second derivative of Brownian motion, I necessarily have that pi 0 itself is up to an additive constant the first derivative of Brownian motion. Because I can deal with distributional derivatives, that's a little lemma, which is perhaps the first lemma in the theory of distributions. I can integrate very much like with regular derivatives. So if I know that derivative of a distribution is equal to 0, I know that the distribution is constant. So from this identity, I learn that pi 0 must agree with the first derivative of Brownian motion plus a constant, and this is not a function, as we have seen. So why is that the most challenging situation? Because if something is not a function, then we cannot make sense of a cube. So the challenge is if pi 0, if the distribution, if the Schwarz distribution pi 0 is not a function, like in this case, then its cube pi 0 cube has no canonical meaning. We can only apply nonlinear operations to functions, in general not to distributions. So the issue is that if I choose psi to be very rough, that this equation here may not make sense, even as it stands, because even in the linear case, even in which I consider to be the best case, even in the linear case, any solution of the linear equation may have the property that I cannot take its cube. Then, of course, I don't expect a solution of the nonlinear problem to be any better. So I have a difficulty with even formulating this equation. So it's not clear how to even formulate star. And it's this difficulty this course will be about, right? I mean, how to give a sense, how to develop a solution theory, how to understand the solution manifold of this equation in such a rough setting. And as you've seen from the examples, kind of the prime natural examples of rough right-hand sides come from randomness. So randomness, as we've seen, like in Brownian motion, is kind of a very natural source of roughness. And the idea is, while randomness is a source of roughness, at the same time, it's also something you can capitalize on. So randomness comes with additional structure. If you stop looking at it in a kind of completely pathwise way, but if you think in terms of the entire probability measure or the ensemble or the law. And that's kind of the guiding idea of what I will present next. Okay, so far any questions? That's the kind of challenge? Yes?
Sorry, a stupid question. Where does this equation appear in the...
Okay, So it's it's an equation. It's a famous equation which appears in mathematical physics, and it's what is called the stochastic quantization of if you take psi to be space-time white noise, and I haven't defined that yet. It's the stochastic quantization of the simplest model in what is called quantum field theory, kind of the scalar Euclidean quantum field theory, more precisely the 5-4 model, and the cube is the functional derivative of phi to the power of 4. I'm more of an applied analysis person. I would say this is kind of the Allen-Kahn equation, which is kind of a standard equation in phase transitions driven by thermal fluctuations, by white noise. So there's also kind of a very applied math or applied physics way of getting to the same type of problem. So it's now here, of course, I present it as, I give it to you and ask you to accept it, but it's clear that it's a very quintessential equation for the entire field. Like there are a couple of other quintessential equations in this business of singular stochastic PDEs, but that might be the simplest representative, in which case I can explain many things in a pretty clear way. But there's no doubt that there is kind of a clear motivation for looking, coming from many fields for looking at this equation. More questions? Yes?
If we change the exponent 3 by another like 2, are we in the same situation?
We're in the same situation. And in fact, surprisingly, much of what I'm going to present here is pretty oblivious to this exponent. There are certain parts of the theory which I'm not going to present, which depend a lot on the exponent. But what I'm going to present is surprisingly oblivious to the exponent. So it's very, I don't know, you may know dispersive equations and the so-called nonlinear Schrödinger equation, where these types of nonlinearities come up, and there is a lot of the equation behaves in a very different way depending on the exponent and also depending on the sign here, focusing, defocusing. Though in what I'm going to present here, that doesn't play a role. So in the end, this cube will be hidden behind a more general structure, which could also incorporate any different power. It's convenient to have it, as you will see in a second, it's convenient for this to be an odd power, and it certainly plays a role that it's algebraic, so that it's an integer. More questions? Yes?
So the phi cube term, is it explicitly introduced, or it's a consequence of a physical phenomena, like you mentioned about mathematics?
Well, in a certain sense, there are different ways of seeing it. In a certain sense, it's the easiest odd nonlinearity which you may formulate. So it's in a certain sense a normal form for many more complicated phenomena, and it's the functional derivative. So it's the functional derivative of the quartic potential, which is kind of a very kind of generic n-harmonic, is the first even n-harmonic potential. More questions? Okay, good. So so now let me return to probably this is better cleaned with that. Let me return to so of course I'm used to wet cleaning, but so let me return to what I said before, that instead of kind of fighting randomness, one should capitalize on randomness. So that's the second section. So a random psi with symmetries in law. So from now on, and that's exactly what's done in these models which come from either applied physics or theoretical physics, we consider this right-hand side to be rough because it's random, but now we want to capitalize on the randomness. So we instead of being given a single right-hand side, we're given we have a kind of a probability measure. So we're given a probability measure or an ensemble. I will use this language interchangeably, or a law on the space of Schwarz distributions. And now we want to capitalize on certain symmetries in law. And the symmetries in law that will play a role are the following. So there's a symmetry by shift, which means that if we shift this random field, this random Schwarz distribution by deterministic shift vector psi, we want this to be identical in law to the unshifted field for all shift vectors in space-time. So that's sometimes also called stationarity. That's, you can easily check that, something which is satisfied, and we'll get back to it, by white noise. And we'll see it in a second, again, in the case of multiple space dimensions. So in a certain sense, statistically, your forcing looks the same everywhere. And that's, of course, a very strong structural assumption one should somehow take advantage of. But that's not the only one. Which is natural to impose, but there are two more which will play a role. And the two others are reflection. So by this I mean that if Rix denotes the reflection of the ith variable, so it's the hyperspace reflection at the linear space where xi is equal to 0, we want our noise to be invariant in law also with respect to this, at least for all the spatial variables. We don't need it for time. So that's the second symmetry, which space-time white noise will have, as we will see. And the third symmetry we can capitalize on is parity, which means that minus xi and xi have the same distribution. So these are three examples of symmetries which you might and we will impose on the ensemble of right-hand sides, on this probability measures out of which we draw our right-hand sides psi. So why are these three symmetries valuable? They're valuable because they are in positive resonance with the symmetries of the operator and the solution manifold. So these symmetries are valuable for our problem for star, which was L phi minus lambda phi cubed is equal to xi in R1 plus D. They're valuable for this problem because the shifted phi solves star with xi replaced by xi plus x. And that's due to the fact that the coefficients of our differential operator do not depend on space-time. So because L has constant coefficients. So because L has constant coefficients, shifting the right-hand side and solving is the same thing as solving and then shifting the solution. These two operations commute. That means, in a certain sense, the solution manifold has the symmetry, and therefore, if you impose the symmetry on your noise, you might hope that you can also recover it on the level of the solution manifold in law. And this holds true for this one too. So the reflected solution is a solution for the reflected right-hand side. And this is due because in terms of the spatial derivatives, they only appear to an even power. So because L is even in del I 1 to D. So that would not be true for I equal to 0. This is the reason why I left it out. And the third observation is that minus phi is a solution to star with xi replaced by minus xi. And that this is a consequence of the fact that the power is odd. Because nonlinearity is odd. So these symmetries are valuable because they reflect symmetries of the underlying PDE or the underlying nonlinear problem, nonlinear PDE, and therefore we have the hope that we should be able to use them. Okay, now let me give this example, which we all should have in our mind, which is space-time white noise, and I think I need to explain it, or it makes sense to explain what this is. So now we work in general D. This is space, time, white noise. And how is it defined? It's a centered Gaussian ensemble on the linear space of Schwarz distributions. Xi. And since centered means it has vanishing expectation, that means it's completely, as a Gaussian ensemble, it's completely determined by its covariance. So I have to tell you what the variance of the scalar, the one-dimensional random variable is, which I get from applying this random distribution to Schwarz function. And the definition is very easy for white noise. This is just defined to be the integral of the square of this Schwarz function over space-time. That's in a certain sense the proper or abstract definition of what white noise is. In a certain sense, it's in a more functional analytic way, you can say it's the Gaussian process of which the Cameron-Martin space is given by the L2 Hilbert space. There's of course a physicist's a way of defining it by saying that the covariance function is Dirac. But let's stick for a moment to this more kind of mathematical or proper way of defining what space-time white noise is. And because this, so first of all, this example has all the symmetries. In law. Why is that the case? Let's start with the last one. Any centered Gaussian field has this parity. Minus the field and the field itself have the same joint or infinite dimensional distribution. So that's obviously satisfied. Now, for the two other symmetries, by the fact that the variance, prescribing the variance like this characterizes the Gaussian, it just boils down to the fact that this expression here is invariant under translation and under reflection. Of course, it's invariant under many more things, but in particular, it's invariant under translation and reflection. So therefore, this invariance of the, if you want, Cameron-Martin space translates to an invariance in law of the random field. So white noise certainly satisfies these symmetries. But there is one other, for us, very important symmetry, which is a scaling symmetry, which I would like to get at. And that will be really kind of a crucial observation for this entire approach. And in order to make it a little bit more palpable, let's return to the case, to the zero-dimensional case, where we know that, or where I told you that white noise can also be characterized as the derivative of Brownian motion. So I guess you all know that Brownian motion has a scaling symmetry, which I can write in the following form. If I take Brownian motion and I speed it up with a factor of r squared, I look at the entire trajectory, at the entire path, then this has the same law as the rescaled Brownian motion, where I kind of rescale length by this fudge factor r for all r between 0 and infinity. That's the standard symmetry in law of Brownian motion. I think you're all used to. Luca Brooks told me that I should always get you, by telling you starting from Brownian motion. So I try to do that. So now, formally, or informally rather, what does this imply on white noise? So at least in a distributional sense, we get white noise by taking the derivative of Brownian motion. And so if we do this, what we discover is that R square is the inner derivative if I take the derivative with x0. R square of the rescaled white noise has the same law as R times white noise. Right? That's just if I apply the, at least completely formally, this derivative operator to this identity in law, and I use the chain rule on the left-hand side, and I use product rule on the right-hand side. So let me just bring this on the other side. And what you discover is this relationship here. And that's an interesting relationship because what does it tell you? It tells you that, let's think of R as being very small. Then this operation here is zooming in. It's a zoom in. So by putting, when you put a variable here, then multiplying it with a small number means you're magnifying, you're zooming in onto your, what is not a function, onto your xi. So you're zooming in, you're blowing up. Zoom in, blow up. And what do we discover on the right-hand side? You discover that as you zoom in, it diverges. So this simple relationship is another way of seeing that white noise cannot be a function, because a function would never have this type of relationship. So this reflects, once again, is not a function. Okay, now let's, in order to prepare ourselves for the multidimensional case, let's do that based on, not in this informal way, but based on the definition of white noise in one space dimension I gave. So properly or rigorously, what this means is the following. So if you test white noise against a test function, a Schwarz function, which you rescale in this way, you get R minus 1 xi applied to the zeta. Yes, thank you. That's a zeta. So this is the proper interpretation of this line, because this operation here is dual to just the rescaling of the right-hand side. So if xi were a function, by the transformation rule, that's what you would get. So let's look at this. Let's look at this side here. So by our definition, that was the integral of Brownian motion against the derivative of this complicated, somewhat complicated object, which I put here. Right? That was the definition which I gave a couple of minutes before. So now by the chain rule, this here makes another factor of R minus 2 appear. And I combine this additional factor, let me call this here with hat. I combine this additional factor here with R minus 2 in order to be able to use the transformation rule, which tells me that this is equal to, that this is equal to minus the integral dx0 b r square x0 d zeta dx0 of x0, with an 1r minus 2 still around. Now I can use this well-known property to see that this is equal, in law at least, to r minus 2 dx b0 r times bx0 d zeta dx0 x0. Now these two things go to r minus 1, so let me continue here. This is r minus 1 times dx0 bx0 d zeta dx0 x0. But again, by our definition, that's the same. So, so this would be kind of the more pedestrian or the rigorous version of checking this identity, which you just got from formally or informally differentiating this relationship. And so it shows you that the value of this formal writing. I mean, it's much more intuitive and quicker than going through this calculation, but you know, you have to start trusting it, so one has to go through this type of calculations. Okay, so so we've seen that white noise has this interesting scaling invariance in law, at least in one space dimension. And now I want to convince you that now based on this property here, that this is also true to some extent. This extends to the multidimensional case. So let me do this. Perhaps I can erase that here, because that was just, it's in, you know, if this is too quick for you to copy, it's in the post-it notes. Okay, so the claim is that the claim is the following. Well, I mean, so before I start to claim something, let's consider a rescaling, a parabolic rescaling. Of time space, which we will use throughout this entire text, Rx, which is equal to little r square x0 r x1 r xd for little r. And in principle, you know, if I liked notation, I would put a little r index here, but you should always think of this being implied, so the kind of the big R is hardwired to the little r by this definition. So why am I looking to this type of strange rescaling? Some of you will know it as the parabolic rescaling. That's how that's the scaling that's compatible with the differential operator L. But in fact, it's also the same rescaling you see here in Brownian motion, right? You rescale the time-like variable with r squared, and you rescale the space-like variable with r. So it's also reflected, but for a different reason over there. So that's a good scaling property. And now the claim is that if we take white noise, so for space-time white noise, and I now write it informally like here. I apply the scaling operator R to the variables. that's this here is the special case for d equal to 0, I get that this in law is equal to r minus d over 2 times psi, where d is 2 plus little d is the effective dimension, effective parabolic dimension of parabolic spacetime. So that's a claim, and I have to convince you that this is true. But if you accept the claim for a second, you notice that not only in higher dimensions, not only do you keep this divergence, it even gets worse. So the higher d, the worse the roughness of white noise. Because the way it explodes, if you zoom in on small scales, becomes worse in high dimensions. Because this exponent here becomes larger as you increase the dimension. Okay, so that's an important observation. And so now let's convince ourselves of this identity here. So now we have to pass via this definition here, and we note that this rescaling is made such if we take a test function, a Schwarz function, and we rescale it like we also had to do in the 1D case by this inverse transformation, and we apply to it the dual operator. So L star is the formal dual, minus d0 plus I1 to d, di square is the dual of L. Then we get that this is equal to R minus 2 times L star zeta rescaled. So that's just the chain rule, and the power minus 2 comes up because L is a second order, or even L star is a second order operation. So this is something I will use in a second, actually not right now. And so let me see where I fit this. I'm going to erase that. So, so let's look at the variance of psi tested against such a transformed test function, and I also put the determinant of this linear transformation r to the power minus 1, zeta r minus 1 dot. So that's an expression we also looked at in the one-dimensional case, where this was just 1 over r squared zeta 1 over r squared dot. So that's the generalization here. So by definition, this is equal to the integral dx hat of the integral of the square of this. So we get the determinant to the power minus 2, zeta square r minus 1 x hat. So that's just mechanically plugging in the definition. Now I want to do a change of variables where I call this here x, and I put 1/2, one of the determinants into the dx, so that I get determinant r minus 1 dx zeta square x. But now this is, again by the definition, the determinant r minus 1 times the variance of psi against theta. So what do I learn from this? I learned from this, so the variances are connected like this. This means the random variables are connected like this. So the law, or let me write it like this. So psi determinant r minus 1 zeta r minus 1 dot in law is equal to the square root of this expression. Determinant r squared minus 1 law of psi zeta. And now what is this expression? The determinant of r is just the products of these terms. That's little r to the power d plus 2. So little r to the power d, and we take a square root. So this is r to the power d minus over 2. And that is just the proper version of writing that psi r dot is equal to r minus d over 2 psi in law. So that proves this scale invariance of white noise, and it's just based, it's an argument which is just based on this definition. So let me close by saying that we wanted to even consider, so clearly white noise is not a function because this exponent is negative. It wasn't a function once, it wasn't a function if you just had the time variable. Now if you add spatial variables, it's more so not a function, it's rougher. But we were interested in a situation where not just the right-hand side psi was not a function, but a genuine Schwarz distribution, almost surely. But we're interested in a situation where also the solution of the linear problem is not a function. So let's understand when that is the case by the following thought experiment. So let's suppose we had a solution of the linear equation. Suppose or consider which has a scale invariance, namely pi 0 r dot is little r to the power alpha pi 0 in law for all r for some alpha, exponent alpha. And we want to understand under which situations is this exponent negative, because if it's negative, then we're also in the case that this solution is not a function, but a distribution. So let's see, that's the following calculation. So we claim that if this is the case, then alpha has to be equal to 2 minus d over 2, from which we learn that hence we are interested in the situation where alpha is negative, which is equivalent to capital D is larger than 2, which is equivalent, larger than 4, which is equivalent that we're in more than 2 space dimensions. And in fact, already the case when alpha is equal to 0 is interesting. So also the 2-dimensional case is interesting. But in order to see this, let me give you the argument for this identity on the exponents, this power counting as it's called. So, and recall that the proper way of expressing this is pi 0 L star zeta is equal to psi zeta for all Schwarz functions zeta. So if we use this piece of information, that identity is easy to see by looking at pi 0 applied to L star, the determinant R minus 1 zeta R minus 1 dot. So on the one hand, we saw from the chain rule which I raised that by applying this differential operator here, because of this rescaling, you get a factor of little r minus 2. So let's put this together with this. So, so by this identity here, this is equal to psi applied to determinant r minus 1 zeta r minus 1 dot. And by the same principle, this is equal to, what did I want? Now here, here I want to use the assumption that we have this, and remember that the proper version of this here is pi 0 determinant r minus 1 zeta r minus 1 dot is equal to r alpha pi 0 zeta. So I apply this here. So this is equal to r alpha minus 2 times pi 0 zeta. And there is the L star missing here. Sorry. I'm getting a bit sloppy here towards the last meters. So this is the L star zeta. And this again, by that triangle, is equal to r alpha minus 2 zeta xi zeta. And this here, by what we just proved, is equal to r minus d over 2 xi zeta. So therefore, these two prefactors have to be the same for all little r, for all scaling factors r, and that can only be the case if the two exponents are the same. Okay, so that gives kind of the interesting or the relevant example for what I want to do, namely consider this equation with a white noise, driven by white noise, in a sufficiently large dimension, so that not only white noise is singular, but also solutions of the linear equation have to be expected to be singular, so that the cube doesn't make a sense. And that, by this kind of dimension counting argument, is the case if d is equal to 2 or larger. And in a certain sense, we will look here at a situation where it corresponds to larger than 2. Okay, so I can take questions. I can kind of give you a little, perhaps before I take questions, I tell you, because I still have, it's 1 hour and a half, right? Sorry? Yes. So I still have a couple of minutes. So let me tell you what is coming up, and then I take questions. So the interesting, so what makes this problem interesting is that, as I said, it doesn't, even formulating the equation doesn't make sense as it stands. And in fact, the problem has to be what is called renormalized. And let me explain in simple words what that means. So that's the third thing, renormalization. And what's called counter terms. So those are two notions which I will explain. So as explained, the equation star does not make sense for psi white noise and d larger or equal to 2. So that's in a certain sense what we learned from this calculation. And so now it needs to be renormalized. And that means two things. So on the one hand, we do something good for us, namely we regularize psi by some sequence psi going to 0, and I will be specific in a second. And on the other hand, and that's in a certain sense bad, we modify the PDE. And so let me be more specific about both. So a simple way of regularizing the noise is by mollification, by convolution. So here we will consider, so here we take the simplest form of regularization. Namely, we will consider psi rho to be psi applied to a convolution kernel of scale rho shifted by x. So that makes sense as that defines a smooth function, provided this kernel is smooth. So where we define this here very much, now let me use the R again, where we define this here very much like we did before. So R minus D psi of R. So that's kind of a Dirac sequence, if you want, of spatial scale R and time scale R squared. And psi is a fixed Schwarz function. So informally, you may say psi is nothing else than the convolution, psi rho is nothing else than the convolution of white noise with this Dirac sequence. And so that fixes the first part. So we want to kind of get rid of the small scale, of the irregularity of white noise by regularizing it. But of course, eventually we want to pass to the limit rho going to 0. And that we can only do if we change the problem. And That's by modifying the PDE. So we modify the PDE by what's called a counter term. So instead of having star, we look at L phi minus lambda phi cube plus h rho phi is equal to psi, again, in all of space-time. So we introduce this strange term, and here I should put the convolution rho, and where this coefficient is supposed to be deterministic. And so since I don't want to go over time, I will explain tomorrow why this ansatz here is natural, because it's the one that respects our symmetries. And the goal of doing this renormalization is that while modifying the original problem, we want to do it in such a way as to preserve as many of the symmetries as possible, but achieving the fact that the solution manifold, which is the object we're interested in, stays under control, stays bounded, or converges to a limit as you let the regularization parameter rho go to 0. So this thing here is expected, in fact, to blow up. And the kind of the topic or the goal of this course is to show that there is a way of choosing this counter term such that the solution manifold converges as rho goes to 0. So that's what I want to explain. That's what I want to explain in the sequel. So next time I will get back a little bit to this one. I will motivate the form why you put this strange counter term here. And then I will start explaining by what set of ideas, and that will lead us up slowly to regularity structures, one can prove this goal here of keeping the solution manifold in check. Okay, let me stop here, and I'm happy to take more questions.